In the name of God, the compassionate, the merciful, engineering plasticity, chapter 4, constitutive relations, part 1. Now, what we learn in this chapter are the answers to these questions. What are the constitutive relations? What do we mean by that? What are the different relationships between stress and strain? How to analyze elastic and plastic behavior of materials? How to apply yield criteria and using the stress-strain relations for real problems. First of all, I'm going to remind you about the elastic stress-strain relationship. Okay, we had these relationships before in the strengths of material and in other courses that you have done in your BSc, and also maybe in some courses in your master course that you are doing now. So what do we have here? That's the modulus of elasticity. Ex is the elastic strain in the direction of x. Why we have used this E, small e? Because we have here elastic strain. When we use the total strain, we use the epsilon. And when we use the plastic strain, we use epsilon p. So that E indicates that it is elastic. So we know that this is in fact the Hooke's law. Okay, Hooke's law. Elastic strain is proportional to the elastic stress. We can divide by E, 1 over E times sigma x minus that. And why is it minus? That's mu sigma y plus sigma z, because if we have the force in the x direction, then we would have strains in the y and z directions, which are the used by this Poisson ratio, shows the different strains in the other directions. In those directions, the strains are negative, they are compressive. If in this direction is positive, in these directions are negative, and vice versa. And so in the other directions also, we have these strain components. Also for the shear components of a strain, we have the modulus of rigidity and gamma yz is equal to tau yz, etc. Right. We could also write these equations in terms of deviator x like that. Sigma x minus sigma m. Sigma m is the mean stress or hydrostatic stress, which is the sum of the stresses divided by 3. Sigma 1 plus 2 plus 3 plus sigma 3 divided by 3, or sigma x plus sigma y plus sigma z divided by 3. And so this is the same as this, because if you put here sigma 1 plus sigma 2 plus sigma 3 divided by 3 here and there, and sum it up, you will get that. So this is just a different way of writing this in terms of the deviatoric stresses, because we call sigma x minus sigma m the deviatoric stresses. Obviously, in the shear components, we have no change. Okay, gamma yz is equal to 1 over 2g, tau yz, etc. And that's what we mean by sigma m. And also we have shown here a component called em, which is the sum of the strain components. Okay, ex plus ey plus ez is equal to em, and these are like that, sigma m over y, because if we add them together, we will get this relationship. This k obviously is the bulk modulus. Okay, bulk modulus. and I have written this again, and we can show these relationships in tensor forms. Eij is equal to sigma ij prime, that's the deviatoric, that is sigma ij minus sigma m, and divided by 2g, so that's sigma prime, and that's this. Delta ij sigma m, that's the Kronecker delta, and this is sigma m, and sigma m is 1 over 3 sigma I, which is this one. Okay, so this is the short form of these equations that I've just written for you. So these are the elastic relationships. Okay, in this course we try to start from the elastic and then go to the plastic part. Right, now these elastic strain relationships also, we could write it in a more generalized form like this. Sigma ij, epsilon ij is epsilon ij over 2g minus 3v, 3 mu divided by E P delta ij. That's the hydrostatic stress or pressure, and that's the Kronecker delta. G obviously is E over 2 times 1 plus mu, and epsilon ij, this is the same thing as we have written in the previous page. Okay, and a more shorthand form is this. Okay, m ijkl, sigma kl, and m ijkl is this. Right, I have written this intentionally because you see these kind of notations in different books, so I just wanted to say these are the same things. Okay, you have to know the tensor notations. And similarly, sigma ij could be written in terms of the epsilon m and epsilon ij, and this is a constant called Cijkl epsilon kl. So that is the Hooke's law. Okay, sigma ij equal to E times epsilon. Here we have written E in a more general form. Okay, this is a very general form, and we call it a stiffness tensor. It's of the fourth order, as you can see, ijkl fourth order, and it has 21 independent components for anisotropic material, and only 2 components, constants in fact, for isotropic materials. Okay, right, so the tensor stress can also be written using Lamé constants like this lambda 2g epsilon ij lambda epsilon kk delta ij, and we call this Lamé constant. Okay, don't confuse this lambda with the lambda that we had before, and we are going to use it shortly. Okay, this is just a notation for the Lamé constant, and here again you can see we have this elastic stress-strain relationship. This is the same thing as before, just different notations. Okay, so far I have explained the elastic relationship between a strain and a stress. In fact, this is the simple Hooke law. Okay, because we have a linear relationship between sigma and epsilon for the Hooke's law. Okay, so this either we put d epsilon ij equal to m ijkl d sigma ij, or we write this sigma ij equal to c ijkl d epsilon ij. We call this stiffness constant, and this is the ductility constant. Okay, let's see what is this constitutive relations. What do we mean? Constitutive comes from construction. In fact, we want to construct relations between stress and strain. Why do we want to do that for the plastic part? Because it's not an easy thing to do, and we have to see how we can construct these relationships. And we use these constitutive relations in solving all kinds of problems, okay, real physical problems. Now we are starting to introduce these relationships. Okay, if you look at these two figures, what I've written here, I'm going to explain. If you look at these two figures, we have a strain and we have a stress. Up to this elastic part, and then this is the plastic part, and then this is unloading. Of course, we could reload here again, like go up here and continue that way. And this is also the same thing, but we have shown on these two figures two different concepts. Okay, in the first figure I have drawn a horizontal line like that, so you can see that we have 2 points here with one value of stress but two values of strain. Okay, therefore you cannot make a straightforward relationship between sigma and epsilon, because we have 2 points here with 2 values of strain but 1 value of stress. Here is the other way around. In fact, if you draw a perpendicular line, then you will see that at a certain value of strain we have 2 values of stress. So this is the same point, but different values of the stresses and strains. That point the same as this point. Okay, but so you can see that what I mean here, and that's why we are working in class where we are going to have these constitutive relations for plastic materials or the plastic behavior of the materials. We use the increments of a strain rather than total accumulated strain. Okay, and that's the reason. That's one reason for it. Okay. Now, one cannot therefore make use of stress-strain relations in plastic region, since there is no unique relationship between the current stress and current strain. We mean here, at this point, there is no straightforward relationship between the strain and stress. However, one can relate the current stress to the current incremental strain. Okay? For instance, if we have a stress here, then we have an incremental strain, and we can relate the stress to the strain. Increment of strain, because happens on a very small two points that are very near to each other make an incremental strain. Okay, so it's almost like a point, and as we make the plastic deformation move on this line, we can relate the increment of strain, not the total, because this is the total strain. That's why we have this problem here. But if we have just a small incremental strain, this problem is reduced almost to zero. Now, these are the stress-strain laws which are used in plasticity theory, okay, based on incremental strain. The total strain can be obtained by summing up or integrating the strain increments. If we take a small increment of a strain here, then we have this equation of the line. We can integrate that incremental strain between 2 points, for instance between here and there, or any other 2 points, and get the total strains between those 2 points. And the part for the elastic, of course, we can use the Hooke's law. Okay, just let me go back here and say that for the elastic relationship, we don't have this kind of problem, because when you load or unload, or start from here and load, you are on the same line. Okay, it's not like that. So we don't have this problem. Okay, Prandtl-Ross equation. Prandtl-Ross equations are maybe the oldest kinds of equations. Of course, we have the Levi-Mises equations, which are given before this with regard to the date, but Prandtl-Ross may be more general. An increment in a strain d epsilon can be decomposed into an elastic part d epsilon E and a plastic part d epsilon P. In the previous slide, when I was talking about the elastic strains, I used the letter E for elastic strain, because in those slides we dealt only with elastic strain. But here, because we are dealing with total strain, elastic strain, and plastic strain, we use this kind of notation. If the material is isotropic, it is reasonable to suppose that the principal plastic increment d epsilon I are proportional to the principal deviatoric stresses. You see, why deviatoric stresses? Because deviatoric stresses cause deformation. We said that yielding occurs only due to deviatoric stresses. Therefore, this must cause the plastic strain. And why they are proportional to each other, and here we have put d lambda, which is a positive number. Why is like that? Because when you get a very small increment of a strain here, it's like a straight line. So it's like this line, okay? And we can write this similar to the elastic or Hooke equation, d epsilon 1 P divided by S1 is equal to d lambda. And similarly in direction 2 and direction 3, these are the principal deviatoric stresses which cause the yielding. And obviously, as we move on the curve, on the plastic curve, this d lambda changes because the gradient changes, a small line. The gradient of that changes. So this is, we call it instantaneous constant, okay? Instantaneous, because as we move along the plastic curve, let me just explain this here. You can see if I get a small incremental strain in here, from say here to there, this is almost a straight line. This is almost a straight line. And then I get another increment here, another increment here. Okay, these are the increments of a strain, d epsilon 1. So d epsilon 1 is this one, and S1 is the deviatoric stress that causes this strain, causes this deformation, okay, shown by a strain. So the relationship between these two, if this is very small, I can get it even smaller than that, this part, this bit, very small. Because these are very small, then I can say that it's like that, because here I have this linear relationship between sigma and epsilon. So I say d epsilon 1 P over deviatoric stress is equal to a constant. But this constant changes because here we have the same straight line for the elastic part. But here is a small increments which we have assumed to be straight lines, they change, the gradient changes. So this d lambda changes as well. Okay. Right. Let's see what we have here. Now this relationship only gives the ratio of the plastic strain increments to the deviatoric stresses, as I explained. To determine the precise relationship, one must specify the positive scalar d lambda. Note that the plastic volume constant is inherent in this relationship. Before going to that, explain about d lambda. Obviously, d lambda we say is an instantaneous constant. For any problem, we should find out this d lambda. That's what I'm going to do in the next slides. Now, what is this volume constancy? Is inherent in these relations because in these relations we have assumed that the hydrostatic pressure does not have any effect on yielding. It means that we have no volume change. Okay, so the material is incompressible. So that's the relationship we have. The epsilon 1p, the epsilon 2p plus the epsilon 3p is equal to 0. It means that the deformation in all directions, if we add all the deformations in all directions, we add them together, is equal to 0. This can be proven if you put equal to constant and take a cubic element for the volume, say A, B, and C, cubic element, parallelepiped cubic element with the sides A, B, and C, and calculate the volume, and then write these epsilon 1, epsilon 2, epsilon 3 after the cube is deformed into, for instance, the sides changed to A plus delta A, B plus delta B, C plus delta C. Obviously, delta B and delta C could be minus. So we just put it like that, and we calculate the volume before and after deformation, so there must be no change. If we subtract these two from each other and put it equal to 0, we will get that. Okay, so this could be proved very easily. Now, Prandtl-Ross equation, so we say is that, and we could also write this Prandtl-Ross equation in terms of the plastic strain increments in terms of Cartesian coordinates, like that. These are principal strains. These are the components of strains. So we could similarly write these equations as well, or in short tensor form we could write d epsilon ij plastic is equal to deviatoric ij d lambda, and sometimes we express these equations in this form. Okay, so d epsilon xx minus d epsilon yy divided by sxx minus syy, like that. There are different kinds of forms for these equations, but this is an interesting one. Okay, this is an interesting one, and it could be seen that oh yes, here if we divide it by dt, we get the rate equation for here. So we get epsilon dot over, because we get this d epsilon dt, so we get epsilon dot minus xx minus yy, etc., divided by sxx minus syy equal to lambda dot. Okay, so note that if we have integrated here as well, so the epsilon d epsilon divided by dt, d lambda divided by dt integration, we get this. So it means that the strain rate also relative to the deviatoric stress is equal to a constant rate. And this brings us to this slide here, which is shown the Mohr circle for stress and plastic strain increment. Here we have the Mohr circle and sigma 1, sigma 2, sigma 3, and also we have put here the epsilon 3p, the epsilon 2p, the epsilon 1p. And why we have put this? Because of this relationship or the previous relationship. Because the previous relationship here, it shows that this is proportional to this. This is proportional to this, the lambda. Or here as well, the epsilon is proportional to Sx. So we could say that, of course, these have different scales. The Mohr circle for stress and Mohr circle for strain coincide with each other because they are just proportional to each other. Okay, so if I take the scale, the correct scale, I can put them together and they coincide. So it means that the epsilon 1 minus the epsilon 2 is equal to sigma 1 minus sigma 2. Okay, so that relationship comes from here. So we showed that there is this relationship between increment of strain, plastic strain, and deviatoric stresses, and therefore we could show that the epsilon xxp is equal to sxx times d lambda. Okay, the first one. Similarly, for these I can write the same. For Sxx is equal to sigma xx minus sigma m, and sigma m is this hydrostatic pressure or hydrostatic component of stress, which has no effect on the deviatoric stress, and it makes no difference with the yield loci, so it doesn't change the volume as well, so that's why we have the volume constancy. So that's sigma xx minus that, and gives us this 2 over 3 sigma xx minus 1 over 3 sigma yy plus sigma zz, because we have here sigma xx minus 1/3, we get 2/3, and we have 1/3 of these two. Therefore Sxx is 2/3 of sigma xx minus half sigma yy plus sigma zz. Therefore, if we put Sxx here from there to there, then we get d lambda times 2/3 sigma xx plus this. Okay, so this is the component of increment of strain, plastic strain. And similarly, I can use these equations, the epsilon yy syy times d lambda, similar to this. I can get this one and that one. Okay, and also the shear components don't change, and this plastic strain law is known as a flow rule. Okay, so here we have the constitutive relations. Of course, d lambda is not known. We will determine that. Okay, so that's the constitutive relationship according to Prandtl-Roth. And note that one cannot propose a flow rule like that. We cannot propose a flow rule which gives the plastic strain increment as explicit function of stress. Obviously, this is not an explicit function. We have this d lambda here, and otherwise Yield criteria might not be met. Why might not be met? Because this d lambda is an instantaneous constant and it's changing. So as the stress increases, this d lambda changes. So this is not explicit. This is just for incremental strain, and it should be determined so that we meet the yield loci at all time. one must include to be determined the scalar plastic multiplier lambda. The plastic multiplier is determined by ensuring the stress state lies on the yield surface during plastic flow. So this is called the plastic multiplier, right? The full elastic plastic stress strain relations are given like that. Okay, so in this part we obtained earlier the elastic components of strains and the relationship between strains and stress, and then we obtained the relationship for the plastic behavior between incremental strain and the stresses. So this is the complete picture of elastic plastic behavior. Obviously, because we have here strain, increment of strain, incremental strains. In here also we have incremental stresses, because this is the elastic part. The elastic part, if you ignore this plastic part, for the elastic part we have a relationship, a linear relationship, Hooke's law, between a strain and a stress. So when we write the increment of a strain, we should write here also increment of a stress. But for the plastic part, we have a relationship between the increment of strain and the stress itself, in fact the deviatoric stress. So that's the complete picture. Okay, that's the complete picture for the strain stress relationship. These equations are called Prandtl-Ross equations. If the first elastic terms are neglected, they are known as the Levi-Mises equations. So these, if you ignore the elastic parts, then we have d epsilon x equal 2/3 d lambda sigma xx minus half sigma y sigma zz, and this is the plastic relationship. These are called the Levi-Mises. Of course, Levi-Mises equations were derived much more earlier than Prandtl-Ross, but because the Prandtl-Ross equations are give us the complete picture, that's why I brought them first. Okay, I presented them first, and nevertheless, these Levi-Mises equations are these, and we can write them in tensor form like that: d epsilon ij, d sigma ij, etc. And now we are going to apply these equations to some simple problems.